Hi everybody, my name is Arthur Marronnier and I'm a PhD candidate in École Polytechnique within the new Paris-Saclay University in France. And today my talk will be about the dielectric properties of hybrid and inorganic perovskite materials used for a new kind of solar cells. My talk will be structured as follows. After an introduction, I will first concentrate on the cesium perovskites, the inorganic perovskites, and here we will only show the results of ab initio calculations. Then I will switch to the hybrid methylammonium perovskites, methylammonium lead iodide more precisely, where we will compare the results of our ab initio calculations and the ellipsometry measurements we did in collaboration with HORIBA company. So first, what is a hybrid perovskite solar cell? Well, to simplify, there are two main generations of solar cells. On the one hand, the mainstream technologies, like this. These are the classic silicon-based solar panels that you've seen more and more on solar rooftops. They have three. First, they are highly efficient, above 20%. Then, they are low cost. They used to be high cost, but their cost has been decreasing more and more. But they are brittle materials. They are not flexible. And that's why a second generation was born, the generation of organic solar cells. And they look, as you can see on the picture, they are totally different from the first generation. They are flexible. And apart from this flexibility, if you compare them to the first generation, they are even cheaper, very low cost. But they could never reach a high efficiency, staying around 10%. Well, now the idea is to do a hybridization of both generations in order to get the best of both worlds, to get the high efficiency of the mainstream technologies and the flexibility of the organic solar cells. And that's where hybrid perovskites come into play. In terms of efficiency, here on this chart, you see the evolution of the different generations versus time. First, the first generation has already reached this very nice 20-25% efficiency, very close to the maximum theoretical efficiency. And it took 30 years of effort to this generation and then to the one of thin films to reach these high values. Then you have the organic photovoltaics, which, as you can see, has reached a plateau around 10% and is not improving anymore. But last, you see this new generation of perovskite solar cells that have jumped in only a few years from 4% to around 20% efficiency. Now, what are these perovskites made of? Well, the perovskite structure in general has the formula ABX3. And in order to have a hybrid perovskite, we have to use inorganic and organic materials. We place an organic molecule for the A atom, which is usually methylammonium, CH3NH3, but in the fully inorganic perovskite, this can be replaced by cesium, and we will talk about these two cases today. Another option for the organic molecule is the formamidinium molecule. Then, this methylammonium molecule that you can see on the picture here at the center is surrounded by inorganic octahedra made of mainly lead for the B part and halide ions for the last part X3. Here we'll be talking about iodide perovskite, but you can also have bromide or chloride. So you can see that you have quite a large number of degrees of freedom in the choice of compounds for these hybrid perovskites for photovoltaics. So are these perovskites the future of solar? Well, they have pros and cons. As I said, they are highly efficient, and there are many explanations for this fact. They have a very high diffusion length, both for holes and electrons, which is quite remarkable. And this length going from 100 nanometers to around 1 micrometer, depending on the structure. They have a high absorption coefficient, even for a wide range of wavelengths. And their band gap, which is around 1.55 for the methylammonium lead iodide perovskite, is suitable for a single cell, but can also be tuned by playing on the halide ions you use, be tuned to around 1.7 eV, for example, which is a perfect value to associate them in tandem cells with silicon solar cells. And they have a very good defect tolerance. So all these points, together with their low cost and their flexibility, the fact that they can be printed, they can be vaporized, they can be on any surface, makes them a very promising generation of solar cells. But on the other hand, they've shown poor stability under different conditions such as humidity, oxygen, and temperature. And today, in general, the stability does not exceed a couple of hundred of hours. Another point is that they've shown a hysteresis in their IV characteristics. And this hysteretic behavior has been mostly attributed to a halide ionic migration inside the perovskite layer, as we evidenced in a work that we published last month, also together with HORIBA company in the Journal of ACS Energy Letters. Now, why are we interested in the dielectric properties of these perovskites, these hybrid perovskites? Well, as far as the dielectric properties are concerned, inorganic and organic compounds behave quite differently. On the one hand, inorganic compounds have Vanier excitance, which means very delocalized excitance, with a low binding energy. And when you look at the formula for the binding energy, it is associated to a high value for epsilon, the dielectric constant. So usually around between 10 and 100. And this is good news in general for photovoltaics, because it means that you don't need a strong electric field in order to extract your free carriers. And it's quite the opposite for organic compounds. They have Frankel excitance, very tightly bound excitance, which is associated with a low value for epsilon, the dielectric constant. And which is in general bad news for solar cells. You need a strong field in order to separate those excitants. So one of the first questions in my PhD was to understand where do our hybrid perovskites fit in this picture. So now on the methods I use for my ab initio calculation, this is your sleep moment if you do not use ab initio in your research. Otherwise, here are some details. To calculate the dielectric constant, I use density functional theory, and more precisely quantum espresso code, using very simple pseudopotentials and the LDA approximation. One important point here is that as you see here at the bottom, I needed very tight conversion thresholds to avoid some structural instabilities I found, especially in the cesium perovskites. I'll come back to this later. Now you have to remember that the dielectric constant depends on the frequency. You have different regimes. In the high frequency regime, you only need to take into account the electronic contributions. But when you go lower in frequency, you'll have to add the atomic and the dipolar contributions, making epsilon go higher for its real part. Well, the high frequency value of epsilon can be directly derived from self-consistent energy calculations. So this is quite easy. But for the dipolar contributions, when you go to a static epsilon in low frequency, this is trickier, and we use the method based on phonon calculations that is details in this article here. And as for the ellipsometry, it's of course in the visible range, so it's only at high frequency that we will be able to measure, to compare actually the calculations and the ellipsometry measurements we did on our own perovskite solar cells. Well, first, let me talk about the cesium perovskite, which we calculated, which dielectric constant we calculated. The perovskite structure is flexible, meaning that it will have different phases depending on the temperature. As you can see, the structure can bend, and you have a tilt angle here, phi, which will change the band gap, by the way. And you have mostly a cubic phase at high temperature, here the black alpha phase, and different orthorhombic phases at room temperature. And here we study both the cubic phase and the orthorhombic phases, mainly the delta phase. So I won't go too much into details about the phonon results that we have, but just to give you one example for the cubic phase, here on the top right you see the phonon frequencies. So you have 15 modes because you have 5 atoms and 3 directions. But one remarkable thing is that we found some negative mode, some structural instability at gamma, at the center here of the cubic lattice. And this is the sign of a anharmonic behavior. So we had to add some anharmonic corrections to our values of dielectric constant. I won't give too much details on this, but this is the work I've done after working on ellipsometry and dielectric properties, and this was submitted last month to GPCL. Well, if we take into account these anharmonic corrections, and we look at both regimes, the high frequency and low frequency regimes, here are the results we obtained. In the cubic structure, we have here the values of epsilon at high frequency, and more interesting are the values at low frequency. In the static regime, you can see that we reach around almost 30 for epsilon. And for the orthorhombic case, it's a little lower. But what is important is that we've shown that cesium lead perovskite, lead iodide, has a high value of epsilon, which is coherent with its inorganic nature. But now what about the hybrid case, the methylammonium perovskite? Well, again, you have different phases with the cubic phase at high temperature and the tetragonal phase being the stable phase at room temperature. What is important to notice here is that the transition from cubic to tetragonal happens at a very low temperature, around 50 Celsius degrees, which is actually a temperature reached during the solvation process, which can be problematic. But here on the calculations, I focused only on the cubic structure. Again, just to show you one result of phonons, as you can see, the results are totally different from the cesium case. You have many more modes, as you have many more atoms in the structure MaPbI3. Ma stands for methylammonium, so many atoms. And one other big difference is that you can see here lots of high frequency optical modes, which are actually the signature of the organic molecule inside the inorganic cage. And you would ask me if, again, we have negative modes around gamma. Well, you can see here on the zoom that we don't have any negative modes at gamma. We don't have the same structural instability. This mode here on the right, negative mode here, is just due to temperature. So it was easier this time to derive the dielectric constant. We don't need any corrections. And here are the results. And you can see that we obtain a quite high value for epsilon static, epsilon 0, around 17, 18, which means that this hybrid perovskite behaves as an inorganic semiconductor, which could explain why it has shown such interesting electrical transport characteristics. Now, in the high frequency regime, we can compare these results with ellipsometry measurements that we did in collaboration with HORIBA using this ellipsometer and making our own cells at Polytechnique. So they were made on top of glass, ITO, and then we use PDOT as an organic whole transporting material and the main absorbing material, methylammonium lead iodide. These cells were made using the one-step wet deposition technique. And as for the ellipsometry machine, we've used an angle of 60 degrees, this range of energies, and to model the optical and to obtain the optical constants, we've used a Torque-Lorentz modeling. Remember that perovskites are unstable, and this is why we've used a seal box provided by HORIBA in order to keep the perovskite cells in a nitrogen atmosphere, which is actually the nitrogen atmosphere with which they were made, in the glove box. So here are the results from our ellipsometry measurements in the visible range. You can see the transition. You have the real part in red and the imaginary part of epsilon in blue. If you look at the real part, you see that the values around 6, 7 are coherent with the values that we found from our calculations around 6 for epsilon infinite. If you look at the imaginary part, which means the absorption, then you can read the band gap. Here, you see that you have a band gap of around 1.5, 1.55 eV, which corresponds perfectly to the theory. Now, from the calculations, we can obtain a similar graphic to compare with this one. And here is what we have. So you can see again that you have globally a good match between calculations and experiments. If now we look separately here on top at the real part and on the bottom at the imaginary part, you see that you have a shift between calculations and measurement. Especially if you look at the imaginary part, you see that the band gap seems to be too low for our calculations. Actually, this results from a trade-off between the accuracy of this black curve and the energy shift we have. If we want not too many oscillations in the black curve, if we want a nice smooth black curve, then unfortunately we're left with an energy shift to the left. But I did some energy band calculations, and I checked that it was the right band gap for our materials and found the right 1.55 value. So we found that for the hybrid perovskite, the dielectric constant is coherent with low binding energies, which could explain why it has such good electrical transport characteristics. This is also coherent with the literature. In 2015, here was published some values from calculations of the epsilon constant in both frequency regimes, and you can see a value around 20. This value is coherent with what we found. We did not find any giant dielectric constant as it was predicted in another article in 2015, also from calculations where they predicted some very high values, 70 for example, for the static epsilon. And as a general conclusion, we've seen that in the cesium inorganic perovskite, we have structural instabilities that have to be taken into account in order to correct the values of the dielectric constant. And that's the next step that we are investigating right now, investigating these instabilities, these anharmonic effects, which could be at the origin of the ferroelectric effects in these perovskites. But in the hybrid perovskite, MaPbI3, we didn't find any structural instabilities. We found dielectric constant around 20 which means that it behaves like an inorganic type semiconductor. We have a good match in the high frequency regime between ellipsometry measurements and our calculations. And one last point is that we haven't here in the calculations taken into account the influence of the organic molecule's orientation, and it has been reported that at room temperature you could have orientation disorder due to this movement. So this could be a next step also. With this, I would like to thank all the people I work with at the University of Paris-Saclay, both from CEA-Saclay and from École Polytechnique, the whole Perovskite team at Polytechnique. My PhD is funded by the French Department of Energy. And I would like to thank Céline and Jean-Paul from HORIBA company for their help, their precious help on the ellipsometry measurements. And of course to thank all of you for your attention. Please feel free to ask me any question. Thank you. Tout simplement.